Very good morning to all of you, dear student. This is a class of our M.Sc final year. Paper is 7th B. Unit is Photochemistry. Unit first. Our this unit is half part of the first unit. Half part has been completed. Now we discuss on properties of excited states. We know that in normal times molecules are lying in ground state known as H0, and some radiations accept and absorb them. Molecules have to go to excited state. That is the first excited state, that is the S1. S1 is known as singlet, and after is T1. T1 is known as triplet. In S1 alignments are same as to ground state, but in triplet states alignments are the different, that is the anti-clockwise or the clockwise. But in S1 that is the anti-clockwise one and one is clockwise. Then triplet in one is clockwise and second is also clockwise. By absorbing UV visible radiations, molecule jump to excited state. Already we know that energy radiation depend upon the frequency of absorbed light and is given by the expression is equals to HNO, that is the Planck constant. Here is the energy of the radiation. H is the not denoted to Planck constant and nu is equals to frequency of the radiation. Excited molecules bring about the photochemical reactions for the synthesis highly strained and thermodynamically unstable compounds which cannot be synthesized by thermal methods. Ultraviolet and visible radiations have enough energy to bring about electronic extension by break the chemical bond. Their energy ranges from 38 to 71 kilocalorie per mole. Excitation from ground state to first excited states can occur in two ways. That is the first way is known as the with the retention of the electronic spin. Retention of the electronic spin, that is the electronic spin are still paired. This is represented as S0 to S1 transition. And second way is that with transition of electronic spin as a result electronic spin to become parallel, it is to S0 to S1, that is the transition, that is a triplet state. Here you know that in this diagram you seen something denoted to E is the energy increase. This is the S1, S0, it's a ground state, and this is the energy level. Here is S1 and this is the energy. After a given energy electrons are on this, but both are same according to S0. But in this stage T1, that is the this is the clockwise, this is also in clockwise, this is the clockwise and this is the anti-clockwise, but here is one is clockwise and other is also clockwise, that is the bonding orbital and this is the anti-bonding molecular orbital. In ground state normal covalent compounds have all their spin anti-parallel. That is the molecules are in singlet state. Even in the singlet state S1 spin of electrons are paired, that is they have opposite spin. Singlet state may be lose energy to give lower energy triplet state. This is known as T1. When spin of electron become parallel, that is the same spin. These two excited states differ in their multiplicities in magnetic field. While singlet state does not split, triplet state may be split in three possible energy states according to the Hund's rule. Multiplicity system with the highest multiplicities has lower energy and it's most stable, that is the T1. Stable is more stable than S1 state. Now some properties of the excited state are being discussed in forthcoming description. That is the first description, that is the structure of excited state. Second is the dipole moment of the excited state, and third one is the acid base strength of the excited states, and fourth one is the reactivity of excited state, and fifth is not photochemical kinetics, and 6 is bimolecular deactivation, that is known as quenching. We discussed on first descriptions, that is structure of the excited states. Greater stability and lower energy characteristics to triple excited state, that is T1, of molecules are attributed to their parallel spin. It is a through it is thought spin inversion during the formation of triplet excited states from singlet state S1 may result in deactivations. A lifespan of S1 excited state is of the range of 10 to the power minus 9 to 10 to the power minus 5 second. Whereas T1 is excited state have lifetime ranges to 10 to the power minus 10 to 3 minus second. Lifetime of singlet excited state, that is tau, is given by the expression tau is equals to 10 to the power minus 5 upon epsilon max. Here epsilon max is known as the excitation coefficient, molar extinction coefficient, at wavelength of which there is maximum absorption. Lifetimes of S1 of ethylene and acetone are estimated below. First, ethylene is known as the maximum absorption 171 due to pi star transition, and value epsilon max for its the 1553 meter square per mole. Therefore, singlet excited state lifetime 4 is estimated as 6.4 into 10 to the power minus 9 second. Second is acetone shows maximum absorption wavelength at 279 nanometer due to the n pi star. Value of epsilon max for its 1.5 meter square per mole. Therefore, singlet excited state lifetime for is the estimated 10 to 6.7 into 10 to the power minus 6 second. This is the lifetime. It is important to note that pi star and n pi star transitions are solvent dependent. If solvent polarity is increased, pi star absorption generally moves towards to longer wavelength bathochromic shift that is known as bathochromic shift, red shift, going to longer wavelength. But n pi star absorptions upon increasing polarity of the solvents show hypsochromic shift, that is the move towards shorter wavelength. The difference in spin of S1 and T1 gives rise to different properties in them. First is the singlet paired state diamagnetic, since all singlet states are spin paired. EPR, electron paramagnetic resonance. Spectroscopy cannot be used for their direction. Second is one, as triplet state have unpaired spin, they are paramagnetic and electronic paramagnetic resonance not given reaction, where paramagnetic quenchers and free radical scavengers like molecular oxygen. As a triplet state consists of a set of three sub-levels arising from magnetic quantum number 0 to plus minus 1, it is split in magnetic field. The singlet and triplet state energies arising from pi star excitation are depend upon that angle of twist about CC sigma bond. The excited states stabilize them to distortion from ground state geometry. In alkane, energy minima corresponds to orthogonal orbital. This is the S1 and this is the T1. Here you can see that they both are same in direction, but one is this and one is this, a positively direction, that is the T1. S1 is same direction, S1 or T1 is the opposite direction. According to Frank-Condon principle, already we know about Frank-Condon principle in previous lecture in unit number first A, photochemistry. According to Frank-Condon principle, excitation is result in excited states with planar geometry, and distortion and rotation about CC bond occur after excitation. Carbonyl excitation produce pronounced geometrical changes. Bond distance CO in ground state of formaldehyde is 0.121. nanometer, whereas excited state bond length is 0.132 nanometer. And molecular geometry changes from planar to pyramidal shape. Having out of plane bond angle is 25 degree. Here you see that S0 is planar. Bond length is 12 degree, 120 degree. But in this second is S1, that is the structure is converted into planar to pyramidal, and bond angle also are changes to 120 degree to 25 degree only, and T1 is also pyramidal but bond angle is the 35 degrees. In first triplet excited states T1, out of plane bond angle further increase and become 35 degree, though CC bond length is not affected. Free radical during photochemical reactions are also excited state, and alkyl free radicals are planar as compared to alkene which are the tetrahedral. Alkenes is on tetrahedral. Bond angle is 109.28 minutes. After that chlorination convert into triangle, that is the 120 degree bond angle. You know that our unit is a dipole moment of excited states. Next topic is a photochemistry. Excited states often have equilibrium geometries rather than ground state geometry. For example, like as acetylene have linear geometry in ground state. This is the acetylene. This is the linear in ground state, but absorbs some H nu. It goes to highest energy level, that is the S1. This is the structure is bent. This is state N1, X1, S1 is the excited state. S0 to S1. Similarly, formaldehyde is planar in ground state S0. This is the planar ground state, but slightly distorted to pyramidal shape in first excited state. Measurement of dipole moment also indicate that geometry changes in excited state dipole moment. Mu is the 2.3 d for the formaldehyde ground state, and it's a 1.5 d is first excited states S1. Dear students, this is our new topics starts from today. This is our last topic of this M.Sc final year in organic chemistry. Already we have discussed on polymer unit number 4, and half part of the unit number 3, that is the some chromatographic techniques, and after we are going to that photochemistry unit number 1. In this pandemic time, you care yourselves and your parents and your friends and your society, and complete studies. You stay in your home and continues with your study, because exams is on the April, in the April maybe according to university, and you use mask in out of your home, and use social distance also, and use sanitize, that is the SMS. S is the sanitizer, M is mask, and S is equal to social distance, because this is the pandemic timing. for the COVID-19 situation. Keep healthy. Thank you so much.